try an experiment. Say you connected a battery with a bulb and you measure the current in the bulb with a sensitive ammeter. What would you see? You would probably observe that at the instant the switch is pressed, the ammeter needle reaches a large value of current and then decreases to reach a lower but a more stable value. This tells you that even at a constant voltage provided by the battery, there is something causing the current to reach a previously higher value before settling down to a lower amount. Since current in the bulb is independent on the resistance of the bulb, it's reasonable to assume that the resistance of the bulb has changed. We'll understand why this happened in this session. Resistance and resistivity depend on many factors intrinsic to the material. The number of free charges per unit volume, the mobility of the charge carriers, and the frequency of the collisions suffered by the electron. Now, the number of free charge carriers in a material is intrinsic to the material. For example, elements like silicon, carbon in its diamond form, and germanium have atoms bonded to each other in covalent bonds. This means that there are relatively very few charge carriers in these materials per unit volume. On the other hand, the situation in metals is very different. In metals, the outermost electrons are so loosely bound to the parent atoms that they behave like a gas diffused in the bulk of conductor, moving freely in all directions inside the material due to the thermal energy. This causes the resistance and the resistivity of these two classes of materials to change in opposite directions in response to an increase in temperature. In metals, an increase in temperature causes an increase in resistivity, or we can say that metals have a positive coefficient of resistivity. Coming to non-metals, an increase in temperature will cause a decrease in resistivity. Therefore, non-metals have a negative coefficient of resistivity. The formula for resistivity dependence on temperature can be given by this equation. Here, rho sub T is the resistivity of the material and temperature T. Rho naught is the resistivity of the material at a predefined temperature T naught, and alpha is the thermal coefficient of resistivity. Here, T and T naught are the temperatures between which the change in resistivity is happening. Now, in this equation, if we transpose rho naught to the opposite side, we get a ratio of rho T and rho naught. Since both the quantities have exact same units, the ratio is dimensionless. In other words, it has no units. Since this ratio is dimensionless, this means that the opposite side of the equation given by 1 plus alpha times the difference in temperature also has to be dimensionless. And since on the RHS 1 is already a dimensionless number, the product of alpha and temperature difference also has to be dimensionless. This can only happen if the unit for alpha is the inverse of temperature. Now we can say that alpha is positive for metals and negative for non-metals. Thus in metals, an increase in temperature will cause the resistance to increase, while increasing the temperature of non-metals will cause the resistance to decrease. Let's see if we can use a mathematical trick to gain more insight into this equation. If we expand and rearrange this equation, we'll get an equation that is very similar to the equation for the straight line. We can also deduce that if the current and the reference temperature are absolute zero, the material still has some residual resistivity. Actual observations show that this is correct, but only for certain metals. For example, let's take nichrome alloy, which is used to make heating filaments. On reaching absolute zero, its resistivity does not drop to zero. Also, there is a range of temperature for which the relationship will remain linear, but not for all metals. And beyond this temperature range, the equation is no longer very useful. Examples of this are copper, which linearly has a non-linear behavior in its resistivity, and semiconductors, which also display an inverse relationship to the temperature rather than a linear one. Now, as to why temperature affects resistivity differently in metals and non-metals, let's look at the equation for resistivity. We can see that the resistivity has an inverse dependency on electron density and relaxation time. In metals, the number of free charges is not really affected by the temperature, so N remains constant. However, increasing the temperature greatly increases the frequency of collisions, and this decreases the relaxation time, causing the resistivity to increase. On the other hand, in non-metals, the situation is very different. Increasing temperature causes the number of free charges to increase by several orders of magnitude, while the relaxation time is not affected very seriously. This increased availability of free charges causes the resistivity of conductors to drop with increasing temperature. Back to the experiment, when the switch is first turned on, the metal filament in the bulb is cold and has low resistance. Thus, the initial current in the bulb is high. But as the bulb heats up to high temperature, its resistance increases, causing a drop in the current. Now let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.